Take two, let's see how it goes. Here I'm looking at systems of equations, and systems of equations are situations where I have multiple equations on the same plane. And that could be two lines that are crossing, a circle that's getting cut by a line, even eventually as complicated as a sphere being cut by a sheet of paper. And we can begin to think of what those slices start to look like. But in this case, we're really stuck in 2D. We're not too worried, but our solutions can take all sorts of different concepts and ideas. But really in this paper, we're going to focus on unique solutions, single solutions, double solutions, that kind of thing. And we'll explain why this is useful in this class as well. We're not just going to do it for no reason. So here we go. Let's do a little y equals mx plus b to put these on the same plane. So I have this starting at 5 and downward sloping line. I have this starting at 8/3 and an upward sloping line. Again, I'm not too worried about being exact on this paper, but what I do notice is these are going to run into each other at some point, and so it's my goal to find that one point. That's what the solution to the system is, because whenever I find that coordinate, I can plug it into this equation, it's true, that equation, it's true. That's the whole reason we're doing this. And when I look here, I notice both of these are equal to y, so why not set them equal to each other? And the rest of this is just going to be algebra. Now that I know that x is equal to 1, I need to go find the other half of my coordinate. So I'm going to plug that back into like a simple equation like this to figure out, hey, it's at 3. 1 comma 3 is where these two lines run into each other. 1 comma 3 is what holds these true. And I'm not going to keep repeating that with every question, but understand, every time we find a solution, it's the place or places that allows everything to stay factual, true, and equal. I head over to this one. The first equation might look a little bit foreign to you guys. It is the equation of a circle. We don't study those as often anymore, but it has a radius of 5. You can see that from the distance formula. You can see that from a little Pythagorean theorem if you wanted to, but that's the idea here. And I have some other line that's going to be cutting through like this. And I notice now I will end up with two solutions, and that won't be too hard to find because when I square root, I'll always get a plus minus. So I'll take this y and plug it into that. If that's what y equals, then this is going to end up in here, watch. Remember, this square you have to be careful with. Don't want mistakes there. Simplify down a little bit. And now I think I'm stuck using the quadratic formula to finish this one out. And here I've come to it. My x coordinate is -2 plus or minus 2 rad 31 over 5. Miserable, ugly stuff. But the worst part is, I have to then go find a y coordinate. And again, I'm going to use the easiest equation I have to do that. But notice, it's going to be this, right? This 2 times that nasty quantity. I might have frozen there. That would make up the y portion. 2 times this yucky quantity plus 1. Onwards and upwards onto number 3. Number 3 starts to show us why we need this. Why would I possibly need to know when two things run into each other? Well, if I have a square root existing on the same plane as a parabola, I might need to know when they run into each other if I have to find the area in between. Again, you're thinking area in between, I need some kind of integral. And for that integral, I need bounds. In this case, upper minus lower, square root x minus x squared. I need to find those bounds. The first one's obviously at 0, 0. And I don't want the next one to be obvious. I'm going to use a little bit of math. I gave you a simple situation to start with. Again, when is the square root of x equal to x squared? I'm not sure. Square both sides. Some of you are probably yelling at me now because I'm doing a little overkill on that, but that's all right. This will give me a solution at 0. This will give me a solution at 1. Those become my bounds, and now my work is cut out for me in terms of integrating. Just wrapping up my integral here, some nice antiderivatives gives me a very clean, very surprising answer of just 1/3. All right, keeping on with this. Now I have 3 equations on the same plane, and I'm going to have to find the intersection and the enclosed area. Again, anytime I have a line, I'm always going to flip it to be y equals mx plus b, because then I'll have kind of that idea that's at 4. I also have this flat line, y equals 4. And then this one as well, what is that, y equals 2x? Yep, so that's going to be sprouting from the origin here. Now, the first thing I notice is like when it says find the enclosed area or the region between, right? I see all sorts of enclosed regions, but the only thing between the 3 lines is this one. All right. Again, you're probably thinking, oh, let me do an integral. Do I want to do dx? Nah, dx is going to be miserable because it's going to switch at some point. I'm going to have to find this other intersection. I'm going to have to find these intersections no matter what. Oh geez. So let's start by finding the intersections. A first coordinate at 0, 4. A second coordinate over here at, what is this going to be? This is y equals 2x. So that's going to be 2, 4. And this one, I promise you I did myself, is going to be 4/3, 8/3. Okay, so I got to find this integral. Maybe you want to go dy. Yeah, let's go dy because I'm doing stars and stripes side to side instead of up and down integrals. So it's going to be bounds based on y. My lowest y value, 8/3. My highest y value, 4. The upper or higher y value is going to be that 2x, but it can't be 2x. It needs to be based on y over 2. And even this other one, the lower bound, has to be based on y. Happy integrating. You thought I was actually going to integrate that thing. Look at this base. This beautiful base goes from 0,4 to 2,4. The base is 2. The height goes from 4 down to 8/3. So I'm thinking it goes from 4 down to 8/3. That means my height is 4/3. Anybody notice that this is a triangle? The area is 1/2 base times height. That's 1/2 times 2 times 4/3. That's just 4/3, y'all. Don't overkill it when you got the easy solution in hand. I promise you get the same answer here. I ended up doing that myself. Flip. Of course I had my rough draft printed out and not my final draft printed out. So I had to do a little fix on here, but your sheet should be fine. All right, so I've got this beautiful graph of sine and cosine. Oops. Where cosine, I know cosine starts at 1, so it does a little bit of this. And sine starts at 0, so it does a little bit of this. Not the finest graph, actually a miserable graph. But what I can tell you is, hey, I found out that they're going to intersect. I did. They're going to run into each other, and this is where pi over 2 is. So it's going to be all right. So I have to figure out where sine is equal to cosine. Anybody have an idea? Everybody knows pi over 4, 0 to pi over 4. I set up my integral. My top is cosine. My bottom is sine. Happy integrating. Take a moment, do it. See, and for a moment I thought I might need to plug in square root 2 over 2, but that would just be wrong, because this coordinate is, when I plug in pi over 4, all right, on to the next one. I know I froze for a moment there, but it's all right. Here we are, casting this forward. I want this to make sense. I want you to see the reason why we're doing these things. It's not just for no reason. It's not just to do Calc 1. It's to really do something with it. I need to evaluate the following double integral of f of xy, that is 2xy, over the region R bounded by this parabola, this line, and this vertical line. Let's do the bounded region first. I have a parabola, I have a line, and then I have this vertical line. So the region that's bounded by both of these is this one, by all 3 of these is this one. Wait, no it's not. It's this one. Wait, it's not. It has to be this one. That was a stupid question. Thank you. All right. So now I need to start defining the integral area. If I need to find the integral of this slice, I'm going to just do some Calc 3 right in front of you. But understanding, hey, this is going to intersect at 1, 1. This is going to intersect at 1, comma 4. This is going to intersect at 0, comma 4. This is going to intersect at 0, comma 0. Really matters. Really matters when I'm doing this. If you could guess. You don't know what all those symbols mean. You don't understand why it's a dA. What does that mean? But trust me, I can tell you that this and seeing this picture makes me understand, hey, I'm going to stay between two functions. I'm going to go dy first and dx second. I'm not going to do all the Calc 3 stuff, but I will tell you is, hey, my y bounds are now stuck between this parabola and 4. But my x bounds would then just be stuck between 0 and 1. Again, that's the Calc 3 stuff, but that's why graphing the region and seeing the region and understanding the intersections matters. It gives me bounds on my integrals that we'll do later. Another one here, maximize the following function given this constraint. Ay caramba, I've done some calc steps for you already, and so it's produced a system of equations with a great new Greek letter lambda that we'll learn about later to do this. So, again, just a system of equation, ignore. Just solve the system. Give me the x and y that makes this true. Well, I can take this one and I can say that, hey, lambda is equal to, no, sorry, not that one. This one, lambda is equal to 2x divided by y. Well, if lambda is equal to 2x divided by y, let's use it here. 2y equals 2x divided by y times x. Well, that gives me 2y squared, which is 2x squared. And what that tells me is y squared is equal to x squared. What that doesn't say is x is equal to y. It kind of does. But it also says x equals negative y. Be careful. Be careful. I go to plug this into my third equation. Why not? I have a whole system. I should use the whole thing. What happens when x equals y? Therefore, y equals plus or minus rad 3. Again, if I wanted to list that as coordinates, but if x was equal to negative y, that's a non-real solution. So when I'm trying to maximize, the possible points of mins and maxes are here. And then I would test those against my function. One more to look at the end, the same kind of thing, the same idea where it says maximize this function given this constraint. That's where the system of equations shows up the most besides finding the bounds on an integral. And this is an especially yummy one. Here we go. I see that x equals lambda 2y, so that means x over 2y equals lambda. Well, if x over 2y equals lambda, that means y equals x over 2y times x over 2. Multiply that denominator over 4y squared equals x squared. A little simplify there. But that means, well, let's look at our third equation. I now have my xy relationship. I've now eliminated how they both depended on lambda to relate to each other. So now I go back here and I say, well, wait, if x squared over 4 plus y squared equals 1, and x squared equals 4y, you can finish out the rest. See, just that easy. Just a little bit of algebra on the end there. Systems of equations are lovely tools that we'll use plenty in Calc 3.